Hello everyone and welcome back. In today's video, we're going to talk about solutions to differential equations. And to get a taste of some of the techniques and ideas that we will be using later in the course to help us to find those solutions. So a solution to a differential equation is just a function that, when plugged in to the differential equation, makes the equation true. A solution is something that makes the equation true, that satisfies the requirement that the equation represents. At the end of the day, if you have a function or if you have a template for a function, if you want to determine if that function is a solution, all you have to do is plug that function in to the equation and see if it makes the equation true or not. Let me give you an example. So here we have the differential equation y double prime minus 5y prime minus 4y equals 0. Now, we will learn later in the class how to solve this equation from scratch, but we don't have those techniques yet. However, despite that, it's very easy for us to determine whether this given function, y equals e to the 4x, is a solution to the equation or not. If I'm given a function and I'm just trying to check whether this function is a solution or not, all I have to do is plug that function into the equation and check to see if the result is a true statement or a false statement. So I'm going to take this guy that's given to me and I'm going to plug in, which means that everywhere there was a y, there is now going to be a e to the 4x. And everywhere there was a y prime, there's going to be a derivative of e to the 4x. And everywhere there was a y double prime, there's going to be a second derivative of e to the 4x. So separately, let me go ahead and calculate that first derivative and that second derivative. The first derivative of e to the 4x is 4e to the 4x via chain rule. The second derivative brings down another copy of 4, so that's 16. And now, if I take that information and plug it into my differential equation here, I find that I get 16 e to the 4x, that's my y double prime, minus 5 times 4e to the 4x, that's my y single prime, minus 4y, that's my e to the 4x, the original function. Is that equal to 0 or not? Now let's clean up what we've got on the left-hand side. I've got 16 e to the 4x minus 20 e to the 4x minus 4 e to the 4x. And if I combine those like terms, I get on the left-hand side negative 8 e to the 4x. Is that the same thing as 0? No, it is not. On the left-hand side, it's an exponential function, and that's definitely not the same thing as the 0 function on the right side. So as a result, I know for sure that e to the 4x is not a solution to this equation. Because it does not make the equation true. Now, what we will find later in the course is that we will have a differential equation and we will have already figured out some template or some format that the solutions will hold. For example, we will learn later in the class the differential equations of this format, like y double prime minus a number times y single prime plus a number times y equals 0. Their solutions have an exponential format, something like e to some number times x. So our task in the later lessons of this class will just be to figure out exactly what value of r should I have here in the exponential to make this template into an honest actual solution to this differential equation. To determine that value of r, all I'm going to do is take this template for the solution and plug it into the differential equation and try and solve for the value of r that makes the differential equation satisfied. Plug in this template, then solve for r. Let me show you what I mean. So r being a value, r being a constant, it's not mathematically much different from that 4 we were working with in the previous exercise. So when I take the first derivative of y equals e to the rx, a single copy of r will come down to the front, and when I take two derivatives, another copy of r will come down to the front. Now I take this first derivative and this second derivative and the original function, and I plug that in to the ODE that I was given. Y double prime becomes r squared e to the rx. Negative 8y prime becomes negative 8r e to the rx. Plus 6y becomes 6 e to the rx. And my goal is for that quantity on the left-hand side to equal 0. Now let's clean up this equation a little bit. Let's go ahead and divide out the e to the rx that is present in all terms. And the equation on the left side then reduces to an equation containing r alone, a quadratic equation that can be solved, for example, using quadratic formula. So r is equal to negative b plus minus the square root of b squared minus 4ac all over 2a. R is equal to 8 plus minus 64 minus 24. So I guess that's 40 under the root, if I've got that right. And so it looks like, after simplification, my r values are r equals 4 plus minus the square root of 10. Just factoring the 4 out of 40, using the square root to turn that into a 2, and then dividing by this 2. So these are the two values of r that are necessary to make this exponential equation, e to the rx, into a solution to this differential equation. So in other words, the functions y equals e to the first r times x and y equals e to the second r times x, these two functions are solutions to the ODE. So this is how it will often happen. We'll have a template for the solutions, and we just need to plug that template into our ODE to figure out the values that fill in the template to make the equation true. To give you another example of this process in action, someone says, okay, I'm thinking of the differential equation y double prime minus 8y prime minus 6y equals not 0, but on the right-hand side, 2x minus 1. And they say, okay, I am aware that a template, a format for a solution to this equation is ax plus b. A linear function will serve as the solution to this equation. So we just need to fill in what is the coefficient of x in the template and what is the constant in the template solution here. So the template has changed and the equation has changed, but the overall process remains the same. I'm going to take this template, plug it into the equation, and use that to determine the values of A and B here. Plug it in. So if y is linear, then the first derivative will just be the slope of the line, this constant called a. The second derivative, the derivative of the constant a, will just be 0. So let's take this y double prime, this y single prime, and this y, and plug all of that information into this differential equation that's been provided here. So y double prime is 0. Then it's minus 8 times y single prime, which is a. Then it's plus 6 times the original y, which is the quantity ax plus b. And I need that to equal 2x minus 1 on the right-hand side of my equation in this problem. Now, if I clean this up a little bit, distributing that 6 on the left-hand side of the equation, I find myself in an interesting situation. I am looking in this problem for two unknowns. I am looking for A and B. And in order to find the values of two unknowns, you need to have two separate equations to form a system of equations that you can solve. Right now, I only have this one equation, which isn't enough data just yet to find the values of the two unknowns A and B. However, what I'm going to do is I'm going to take this single equation that we have found by plugging my template into my ODE, and I'm going to split this into two separate equations. I'm going to split this single equation into two separate equations by looking separately at the terms containing x and the terms that do not contain x. So for example, in the equation that I'm given, the constant terms tell a story of their own. That negative 8a, that term that doesn't contain x, plus 6b is on the right-hand side matched to this constant negative 1. So the constant terms tell the story negative 8a plus 6b equals negative 1. Now separately, if I look at the x terms, and if specifically I look at the coefficients of the x terms, the coefficient attached to x on the left-hand side is 6a, and the coefficient attached to x on the right-hand side is 2. So by looking separately at the coefficients of x and separately at the constant terms, I have now gotten two equations that I can solve for the two unknowns that I need to fill in my template, the two unknowns A and B here. So I find from that first equation, pretty much right away, you can find that A must be equal to 1/3 from 2 divided by 6. So plug that into the second equation, and I find that negative 8 times 1/3 plus 6b must equal negative 1. So if my algebra is on point today, if I take this negative 8 times 1/3 and add it to the right-hand side, I get that 6b must be equal to, I think, 5/3. And then dividing by 6, b must be equal to 5/18. So these are the values of a and b that would cause this template solution to be an actual solution to this differential equation. In other words, the function y equals a equals 1/3 x plus b equals 5/18 is a solution to the differential equation. So that's what solutions are. They're just functions that make the differential equation true. And often you will have a template or a format for the solution. And by plugging in that template, you can deduce the values that have to go into the template in order to make that format work for you. Let's proceed to the second half of today's talk, where we introduce the concept of an initial value problem. An initial value problem consists of a couple of different requirements or stipulations. An initial value problem is a differential equation that must be satisfied, plus at least one initial condition that must be satisfied as well. Just to give you a simple physical example, we studied in lesson number 1 the differential equation that was associated with the spring mass system. So for example, with y of t being position, we found that mass times acceleration was equal to net force coming from the spring's restoring force and coming from air resistance or damping. Now, if you also know that your object had some specific initial position and some specific initial velocity, then you would add those initial conditions to the collection of equations that's describing what's going on in this physical situation. And so just on the left-hand side, we have the differential equation, but now with these two initial conditions, we have what is called an initial value problem, a differential equation plus at least one additional condition that must be satisfied. Now, when you're solving an initial value problem, any solution to that initial value problem must be a solution to the differential equation, but at the same time, it must also satisfy the initial conditions given. It must satisfy all the initial conditions. When you're talking about an initial value problem, any solution to such a problem must satisfy all the criteria that are given. If even a single one fails, your solution is not viable. So for example, I can ask, okay, here's an initial value problem. Y double prime minus y equals 0. There is our differential equation, and we also have two initial conditions. Y of 0 must be equal to 1, y prime of 0 must be equal to 2. Now, if y equals e to the x is going to be a solution to this initial value problem, all three of these conditions must be satisfied. So let's check each of them one by one. I'll start by finding y prime and subsequently y double prime so that I can check whether this function is a solution to the differential equation I was given. So y double prime gets replaced with e to the x, then minus y, which is also e to the x. Is that equal to 0? It sure is. So the first condition is satisfied, no problem. Next, I will check the initial conditions. So let's plug 0 into the original function, e to the 0. Is that equal to the given requirement, 1? It sure is. No problems there. But when I plug 0 into the first derivative, e to the 0 is not equal to the 2 that it's supposed to be in the second initial condition, which means that the second initial condition has failed. So because this function did not satisfy all three of these stipulations, this function is disqualified as a solution to this initial value problem. E to the x is not a solution to the initial value problem, even though it was a solution to the differential equation. So bearing that in mind, what you will often find, once again, when you're solving initial value problems, we are going to have some template or some format that we know our solutions are going to have. So to give you an example, I'm solving this initial value problem, y double prime minus 3y prime plus 2y equals 0. We also require that y of 0 equals 4 and y prime of 0 equals 3. Somehow, we'll talk more about this later, we have been provided with the template y of t equals some constant c1 times e to the t plus some constant c2 times e to the 2t. And we're told that this is a template for a solution to this initial value problem. We just need to figure out what values we should have for the constants C1 and C2 to make this template into an actual solution. So to that end, what I'm going to do is I'm going to plug in this template to the differential equation and to all the initial conditions, and I'm going to use that information to deduce what values C1 and C2 should hold. So to that end, I'm going to go ahead and calculate the first derivative and the second derivative using the traditional rules of working with exponents. So our first derivative is c1 e to the t plus 2 c2 e to the 2t. And then the y double prime will see a second 2 dropping down from that exponential in the back. Then I'm going to plug that information into my differential equation to see what is happening there. So let's check the ODE next. So y double prime goes in, c1 e to the t plus 4 c2 e to the 2t. Then I have minus 3 copies of y single prime. Then I have 2 copies of my original function, which was c1 e to the t plus c2 e to the 2t. And I want to see what is it going to take in order to make that entire left side equal to a 0 in the end. Now, if I do a little bit of distribution and I gather some of the like terms together, so c1 e to the t, negative 3 c1 e to the t in the back plus 2 c1 e to the t, and look at the other terms, plus 4c2 e to the 2t minus 6c2 e to the 2t plus 2c2 e to the 2t, and gather those like terms together, what I see is that all the terms on the left side always cancel out no matter what. Here's plus c1 plus 2c1 minus 3c1, so those cancel. Here's plus 4 plus 2 minus 6, that cancels as well. So this first requirement is satisfied no matter what the constants are. So we won't get any information about these constants from the differential equation. So instead, let's turn our attention to these two initial conditions, and let's see what information these two conditions imply about what C1 and C2 must equal. Next, check the initial conditions. So the first stipulation is that when we plug t equals 0 into our function, the result of that needs to be equal to 4. So if I plug t equals 0 into my template, then these e to the zeros will each become 1, and I get c1 plus c2 on the left-hand side, and I require that to equal 4 on the right-hand side. The initial conditions also require that when we plug 0 into the first derivative, the result is equal to 3. So to reflect that, I'm going to plug 0 into this first derivative of my template, and I'm going to set the result of that equal to the specified 3. So now I have two equations forming a system that I can solve for the two unknowns, C1 and C2. I can take this first equation and apply, for example, a minus 1, and then add it to the second equation, which will give me C2 equals minus 1. And then I can plug that back in, for example, to equation number 1 to say that C1 minus 1 equals 4, so C1 must be equal to 5. This with a little arithmetic there. So from those initial conditions, we've found that the C1 and the C2 in the template must hold these values. So in other words, the function y of t equals the C1 we just found, e to the t, minus the C2, e to the 2t. This function is a solution to the entire initial value problem.